So I'll talk about superconducting circuits for quantum information processing, and there will be more talks on that subject area later today, and in particular Honey Pike from IBM will talk a bit about what their company, there she is, yeah, okay, I am waving, hello Honey. So she will present what IBM is doing in this area and how they make their systems available in the cloud for you to program. So since I'm then the first speaker on that topic, I'll use some of my time to introduce how to work with electronic circuits quantum mechanically. So that will be the first part of my talk. And then in the second part of my talk, I'll present a set of recent experiments that we have done that I think may become, that I hope are interesting already now, yeah, for their basic science, but may become important at a later stage in quantum information processing. And so there's a nicely ray-traced picture of the idea of it on this title slide. So there's two chips that you see in the two corners of this slide here. And the question that we were trying to address is the one where we ask ourselves, okay, how many qubits will you eventually be able to fit on a single integrated chip? And I think as of now, we know how to do maybe hundreds of qubits on the same chip, maybe 1,000 or so. But how we can do thousands or millions on the same chip is not yet clear for superconducting circuits. I don't think that any of the academic or industrial partners have a really clear idea how we will make this transition to go from tens or hundreds to thousands and then millions of qubits. And so one of the aspects that could be interesting, similar as if in the case that you look at when you want to increase computing power in your current computer center, you're trying not to build one single larger computer, but you make a computing system, a cluster, which connects many of your computer modules together into a larger cluster of computers that gives you then more information processing power. And if you want to transfer that sort of idea to a quantum information processor, the different modules of the quantum information processor have to be able to share quantum information coherently. Yeah? So you have to, say, create entanglements between two of your quantum computers that may be sitting in your computer center, and you have to be able to exchange quantum information between these computers. So that's the basic element for that. That's something that we've worked on a bit, and that you see here. So there's this one chip and the other chip, and the goal is to take a qubit on one chip, have it exchange quantum information by exchanging single photons with qubits on a different chip. And to make that work well at high fidelities, actually took some thinking and then also some effort to make it work. And that I'll be presenting in the second half of my talk. Okay, so the title is very general. It's quantum information processing with superconducting circuits. And the current team here at ETH is listed, and our theory collaborators that worked on this entangling qubits across chips project. And so our funding comes from European sources, from Swiss sources, and so we are part of this, one of these just newly started European programs on quantum information processing, which is called Open SuperQ. And we also work with US funding agencies on error correction schemes. And indeed, those guys are meeting up just yesterday, today, and tomorrow in Dallas to have a technical exchange meeting about the state of the art in quantum error correction. Okay, so I've been in Zurich now for almost 13 years. Yeah, so time passes quickly, and so since that time we've collaborated a lot with labs at ETH and also elsewhere. And there were also a fair number of students who've worked in our lab and who've then moved on, some to faculty positions, but also others who now work at IBM and Rigetti and elsewhere in quantum information processing. All right, so first thing, so I'll start very basic and maybe even embarrassingly simple, and it's probably not might not be needed for this audience, but why not start at this basic level? So what we're essentially trying to do is we're trying to build circuits that behave quantum mechanically from circuit elements that you all know, yeah, that are conventional circuit elements like capacitors, inductors, resistors, maybe nonlinear elements such as diodes. And these circuit elements you usually don't think of as behaving quantum mechanically. Yeah? However, they do form sort of the basic elements of integrated circuits that we use, and they've come a long way from inventing the first transistors a long time ago until integrating really many billions of those on a single chip. And so while maybe for understanding the materials that are used in these chips, like the semiconductors, you do need quantum physics for that to understand the band structure of a semiconductor and compare it, for example, to the band structure of an insulator or a metal. For the information processing on these integrated chips, usually it's sufficient to think classically about the physics that is involved. Yeah? There's no quantum mechanics, no superposition principle, no quantization of fields. And nevertheless, IBM and Rigetti and others and many academic research labs use these circuit elements to build quantum things. So why is that? So here are these basic circuit elements again, and so one way that I think is quite intuitive to think about it is, okay, so you take a conventional capacitor, and the currents and charges that, or the charges that you can put on this capacitor are quantized, yeah, because the charge is not a continuous variable. In that sense, it comes with in units of single electrons. So if you take a single electron, you could place that electron on either the lower or the upper plate of that capacitor. Yeah, and classically, you have these two different options. Yeah, and quantum mechanically, the same electron could be, so to speak, simultaneously on both of these capacitor plates. So it's in a superposition state. So this the superposition state, if you could write pictorially as a sort of a coherent superposition of the electron being on the lower plate and on the upper plate. And if you believe in quantum physics of microscopic objects, yeah, which I think most of or all of us do, we learn about it, and we learn about the hydrogen atom, and so that seems sort of natural still. But maybe to think about it in the context of electronic circuits is something that you're maybe not used to. So another situation that you could think about is if you had an inductor included in a loop. Yeah, you could consider a current flowing through that loop, and that current will be made up of maybe many millions or even billions of electrons. And so classically, that current could flow clockwise or counterclockwise, but quantum mechanically, the current could be in a superposition of flowing clockwise and counterclockwise. And that already is a little bit less intuitive if you know about quantum mechanics, yeah, because now you have a sort of a macroscopic variable and maybe a macroscopic current that can be in a superposition of states. And again, you could write this as this wave function here. And in fact, in the mid-80s, research on superconducting electronic circuits started out with this question whether macroscopic variables like the current flowing through these circuits could show quantum physics at all. And it was not really clear whether the answer to that would be yes, because no experiments had been done. And so in the mid-80s, then first experiments tried to look at quantization of current in superconducting circuits, energy level quantization, and also quantum mechanical tunneling effects. And I also tried to look at whether they could observe these superpositions of currents. And in the mid-80s, that really failed, and people didn't quite understand why, and there were also already people at IBM thinking about this problem. But then high-temperature superconductivity came along, and nobody cared about this anymore until the ideas of quantum information processing became more prevalent, and people started to think about superconducting circuits for realizing quantum computers again. Okay, so maybe one of the ways how I like to think about these electronic circuits and why they can be described quantum mechanically and why they behave quantum mechanically is through this analogy between sort of charge and flux in an electronic circuit and position and momentum for a particle in free space. Yeah, sort of roughly the first thing that you learn in quantum physics in your introductory course. Yeah, you look at problems of sort of wave-particle duality, and you describe a particle moving in free space and being assigned a position and having a momentum. And you know that there's an uncertainty relation for position and momentum. Yeah, there's a Heisenberg uncertainty relation between these two. And position and momentum are conjugate variables to describe the motion of particles in three-dimensional space. And so it turns out for electronic circuits, charge and flux are the equivalent conjugate variables. They're like position and momentum, but for electronic circuits, charge and flux are the conjugate variables. So indeed, it's the fact that for these conjugate variables, charge and flux, a similar uncertainty relationship holds. And so you could do everything that you are used to do for sort of motion of particle in free space, how you go from writing down the full energy and the Hamiltonian and say the classical Hamiltonian function and then promoting that to a Hamiltonian operator. You could do in the same way for electronic circuits by writing down the electric energy in terms of charges and the magnetic energy in terms of fluxes, write down the total energy and then quantize these variables, charge and flux, and get the Hamiltonian and stick it into a Schrödinger equations and find the energy levels of an electronic circuit. So that's really the basic way how you think about the quantum physics of these electronic circuits. And so two very important elements in the context of superconducting electronic circuits for quantum information processing are still very, very simple. So when you combine an inductor with a capacitor, either in parallel or in series, they form a harmonic oscillator. And the frequency of that harmonic oscillator is set by the inductance, by the size of the inductor and the size of the capacitor. And this combination of inductance and capacitance typically gives the electrical circuit resonance frequencies in the order of a few gigahertz. And it's that frequency that all the superconducting quantum information processors work at, yeah, a few gigahertz. And so that's then a harmonic oscillator, and it's the classical Hamiltonian is quadratic in the flux and quadratic in the charge, yeah, and therefore you know it's a harmonic oscillator Hamiltonian, and you know how to quantize that. Yeah? And also for an electronic circuit, you will then just find the harmonic oscillator rules for quantization. So there's energy levels labeled by a quantum number from 0 to n, and the separation between the energy levels is just Planck's constant times the resonance frequency of this circuit. Yeah? And so that's a linear oscillator. And if you want to, you can think about that as sort of a microwave frequency analog of a resonator storing individual photons. Yeah? So the excitations here in this harmonic oscillators are photons living on this harmonic oscillator LC circuit. So what is important is that not everything stays linear. Yeah? If you combine these circuits together, then anything that you could build would just be a combination of harmonic oscillators. But to create quantum mechanical systems, it's actually convenient if they also have transitions that you could address individually. And one of the problems is that in these linear oscillators, you can't really address any transitions individually because the separation between 2 and 3 is the same as between 0 and 1 and any of the other neighboring states. And so one of the ways how to get around that in superconducting circuits is to replace this linear inductor here, in which the flux created by a current flowing through that inductor is linear in the current. You can replace that by a superconducting circuit element which is called the Josephson Junction. And in that nonlinear element, the current flowing through the junction is a cosinusoidal function of the flux that current creates. And since this relationship is nonlinear, it will create a nonlinearity in the Hamiltonian. And the consequence of that is that the energy level spectrum now has not equidistant energy levels, but has energy levels that have different spacings from each other. So in particular here for this type of unharmonic oscillator with the linear inductor replaced with the Josephson junction, you find that the separation between the first and the second excited state is by alpha smaller than the separation between the ground and the first excited state. And that allows you then to use microwave frequency pulses, pick a transition frequency and just change the occupation of these states that are linked by that microwave frequency difference. And you can also write down the Hamiltonian for that if you want to. And so basically these unharmonic oscillators in combination with these harmonic oscillators are the elements that you use in all quantum information processing with superconducting electronic circuits. Okay, and so so I told you there were first experiments in that direction were done in the mid-80s, And then there was a big breakthrough in 1999 by Yasu Nakamura at NISQ at the time, who built the first superconducting qubit out of this, where you could really see a superposition of charge states, where a charge could be in two different parts of the circuit at the same time. And since that field really developed quite dramatically. And here you see pictures from circuits that people built in academic labs. And I do think that probably by now you have, I think, close to 100, maybe it's already more than 100 different academic labs worldwide that work with these circuits and explore their quantum physics also for the applications of quantum information processing. And so one of the aspects that maybe changed in the past few years then is also that not only academic institutions are interested in this field, but also industry got interested. And IBM itself always had an interest in superconducting electronic circuits. And so I think also around 10 years ago, they started to explore more seriously the possibility of building quantum information processors. And you'll hear more about that from Han-Hee later. Okay, there's not only IBM, but there's also Google, who took out an academic effort from UC Santa Barbara and essentially has their own activity on this now. Okay, there's D-Wave, which is a startup, or not, okay, a company that was founded 20 years ago as a startup that is making a special kind of system for quantum information processing. There's startups like Rigetti Computing, and sort of one of the stories that I used to tell on that also is that Chad Rigetti, the founder of this company, and I used to play soccer in the intramural league at Yale or so, and now he has $100 million from venture capitalists to try to build quantum computers and be a competition to these guys here. And then there's also Microsoft and Intel and others are certainly also interested. So this large presence of industry is definitely having an impact on the field, and you'll hear more later. Okay, so where are we? So industry and startups are now having superconducting electronic circuits that combine maybe, say, several tens to maybe about 100 of these circuit elements, superconducting qubits and superconducting resonators on integrated chips. So here you see one from Google. Here you see a picture of a chip from IBM and one from Rigetti and one from Intel. So one thing that recently happened is that here the IBM chip you still see from the front side, and the other ones here are now clever, so they don't show their chip anymore because they have some flip-chip technology. So the actually interesting parts are below here because they've separated the wiring layer from the qubit layer. And so there's people are working with several tens of qubits, and I think IBM has things available in the cloud with up to 20 qubits and working on chips with more qubits. But it's actually a fairly big challenge to have these larger chips with larger numbers of qubits work properly. Yeah? And I think Google, for example, maybe more than a year and a half ago, announced that they would soon have a chip with say, I don't know, 50 or 70 qubits, and do implement some algorithm that would show quantum supremacy. Yeah? And but it took them longer to get things going than they thought, and we're looking forward to see what the next results there will be. And I think one of the problems is really that these largely integrated circuits, you have to deal with the way how the different circuit elements affect each other in a more analog way than we're used to from digital circuits. So it's actually a quite significant challenge to make these circuits larger. And I think it's also not really to be expected that within the next few years we have really systems with many thousands or hundreds of thousands of qubits that work well. So it will require more work, I think. Okay, so what are people doing with superconducting circuits just right now? I would say, if you ask yourself, okay, does a superconducting quantum information processor exist? You could have probably already, quite a number of years ago, said, yes, it exists. Yeah? So there are circuits which have everything that is needed: qubits, single qubit gates, two qubit gates, qubit readout, demonstrations of little algorithms. So they existed since some time, and basic algorithms have been demonstrated on these circuits. And so now the goal is to start doing something interesting with these circuits. And one of the key elements is to try to error correct these circuits, because error correction will always be necessary in these systems, both also for fundamental or predominantly for fundamental reasons. Also, if you build the perfect circuit, quantum physics requires your excited states of this circuit or the excited states of the qubits to decay to the ground states due to their coupling to the vacuum fluctuations. And vacuum fluctuations of electromagnetic fields are unavoidable, so any quantum computer has to be able, any universal quantum computer in the end has to be able to correct errors. And so that's one of the areas that there's put a lot of effort in. And how does that work, basically? So you start out essentially with a single qubit, and if that was perfect, you could just use it as the information carrier and not worry further about it. But since there are these effects like spontaneous emission or coupling to vacuum fluctuations that causes it, what people chose to do is to introduce redundancy in these qubit systems and to implement quantum error correction based on them. So rather than using this physical qubits that can decay, you can encode a logical qubit in a larger number of physical qubits. And one thing that you could do is you could use surface code, and which is an encoding scheme, and use this kind of checkerboard pattern of qubits to try to run a very specific set of operations on these set of qubits to detect when errors happen and to be able to correct for them. And that is based on parity measurements that you do on data qubits. So here the black dots represent data qubits and the white dots represent ancilla qubits, and you perform parity measurements between these ancilla and the data qubits, and if you are able to interpret these parity measurements, you can actually detect whether an error happened and then correct for it. And then to do quantum information processing, you would combine many of these logical qubits into a larger fabric of qubits, where you then do logical gates between logical qubits. And so one of the views that you could have is, okay, you could take several of these 17-qubit logical qubits and put them into this larger scale circuit. And so here you already see one of the challenges. So if you now have, say, a quantum information processor with 50 qubits or so, you will be able to encode in that maybe 3 logical qubits and then do algorithms on 3 logical qubits, which is a good conceptual thing to show, but with which you will not yet solve any really interesting science or computational problems. And so while that is needed for building a large-scale universal quantum computer in the long run, we also need to figure out whether there's any interesting problems that we could solve with just using 50 or 100 qubits without error correction. And in superconducting circuits, there's quite a bit of activity to use those kind of circuits for digital or a combination of digital and analog quantum simulation. And there's really sort of basic, very basic examples of them that have been implemented, say solving spin models using superconducting circuits, or looking at these electrons in 2D, which is a result from Santa Barbara, or simulating other sort of physics-related Hamiltonian properties of physical systems, but not by looking at the physical system itself, but by making a simulation based on superconducting circuits with it. And maybe one thing that I guess Hanhi will then talk, Hanhi Paik from IBM will talk more about, is that one of the simulation goals that people are currently finding most interesting is to use superconducting quantum information processors to perform quantum chemistry simulations, to essentially try to find the ground states of currently simple molecules, but maybe in the future more complicated molecules that you're interested in knowing the properties of. Okay, so these are the two main application areas. Yeah, trying to build error correction into these circuits for eventually having a universal superconducting quantum computer, and trying to use the architectures which you have and the size scales of chips which you have to to perform or to solve interesting problems. Yeah? And goals are to identify more of these interesting problems and to scale your circuits in a level that you can maybe address questions that would be hard to address on a conventional. Okay, so at this point I would then switch to this other part of my talk, in which I will present you like our approach to think about how to couple two physically separated superconducting chips with each other. And for that purpose, not so long ago, like maybe 2 years back or so, we started to develop some very specific superconducting circuit elements that are interesting for that purpose. And so we now have an architecture that maybe in the beginning we didn't really quite know that it would go along with us a long way, but now we've actually seen that that was a good investment. So with this single idea, we've actually realized a very fast and high fidelity single shot readout for superconducting circuits. And I think currently, if I'm still up to date with it, I think we have the fastest readout with the highest fidelity. So it's just a little bit less than 50 nanoseconds. You can achieve 98% readout fidelity. And we really forced ourselves to have that readout to happen fast. Because, for example, one of the application areas of that would be in a surface code with error correction. Every error correction cycle, you have to read out your ancilla qubits. And if your gates are fast, that's good. But if your readout would be slow, then you waste a lot of time, a lot of your valuable coherence time to have that readout completed. And so to reduce the readout times to timescales that are similar or below the times that you use for logical gates is very important. Then these circuits we can also use for performing an unconditional reset. Yeah, after these ancilla manipulations, you need to reset your ancillas, you need to initialize all the qubits in your quantum information processor in the first chip. So one thing that will be needed eventually is to realize multiplexing in these superconducting circuits. So currently it's more or less like every qubit is addressed individually through its own wires, and you need to be able to reduce the wire count and multiplex. And then we have done some recent experiment where we implement parity checks with feedbacks that are important in this error correction context. And that's something that the guys sort of in the other time zone in Dallas are currently presenting, but which I won't have time to talk about today. And what I will talk about is this remote entanglement and deterministic state transfer protocol. And actually the same thing you can also use for single photon or quantum number demolition, single shot, single photon detection, which is also interesting, which is maybe not in the context of quantum information processing. Okay, so let's start with this first little bit on this architecture because it's an important element. So here's a sort of a zoom in on that chip. Yeah? So that chip is not very integrated, it just has a single qubit. So you will not compute anything on that chip, but you can test these information transfer and entanglement generation protocols. So here's a superconducting qubit. It has two electrodes, the orange ones, the top are like one electrode here and a second electrode there. And these two electrodes are connected by two of these nonlinear inductors, the Josephson Junctions, which form a loop. So then this qubit is connected to two sets of resonators. So there's a set of resonators at the bottom, like here a lambda quarter superconducting transmission line resonator, which is essentially a long wire on this chip, which is shorted on one end, and then has a resonance frequency of a few gigahertz, and it's connected essentially to a filter here at the bottom. And through these two, through the resonator filter combination, you can actually measure this qubit state here by measuring the frequency shift of this resonator here when the qubit changes its state from ground to excited state. And that here typically gives you a frequency shift of the resonator by a few megahertz or maybe even around 10 megahertz. And then you can, by sending a microwave tone towards that resonator, you can detect that frequency change and use that to, with high fidelity, map that frequency change to the qubit state. And so we optimize the parameters of this chip here to create very fast and very high fidelity readout. So that's a geometry, this combination of qubit and readout resonator with this filter we also use for our entanglement generation protocol. And indeed this circuit here has another set, essentially a copy of these two resonators here on the top, and that we can actually use to have that circuit, that qubit here, emit its excitation as a photon in this into this resonator, and then the photon can leave through that port and can exit the chip, and then we can take that photon and guide it through a long microwave cable to a second chip and then reabsorb it there. Okay, I said that the same structure you can use for resetting, and I don't have time to explain that a bit, but I would like to show you that it's multiplexable in some form. So here's a chip that we have realized at ETH. So it has 8 qubits, so the red cross-like structures which you see here are 8 qubits, and the 8 qubits are labeled with these Q1s to Qn, and each one of them has a combination of this readout resonator and this filter structure. And one of the interesting multiplexing bits is that you can read out all these 8 qubits simultaneously through this one yellow readout line here. So, and that's, for example, one of the ways how you can save infrastructure for building your quantum information processor. So now for something where you might have needed 8 readout lines before, now you can get away with 1. And this type of multiplexing needs to be implemented for superconducting circuits much more. And so this realizes a linear chain of qubits, and they're coupled to their nearest neighbors through these coupling microwave frequency resonators, which are essentially the linear resonators that I've talked to you about before. Okay, and so how to use that for this remote entanglement and state preparation protocol. So here's essentially a little picture of how that works, like an atomic physics representation of the qubits and the resonators on 2 physically separated chips. So there's 1 qubit and a resonator on one chip, and another qubit and a resonator on the other chip. And we think about them as nodes of a quantum network, and at every one of those nodes we would like to store and process information, but then the nodes should also be able to send information and receive information. And that could be good for expanding quantum processors, performing error correction across different nodes, and creating distributed entanglement for communication using repeaters. And you want that link to be coherent and deterministic, and you would like to work it as often as possible so that it creates a high data rate. Okay, and this is obviously a problem that has been worked on, and interestingly, it has been worked on every quantum system that you can think of, more or less. Yeah? And so here's a list of the quantum systems, and a not complete, but a list of papers that has made contributions in this area. And there's really many different protocols with which you can exchange quantum information between sort of 2 physically separated sites that are based on different physical phenomena. But one of the problems is that many of these protocols were probabilistic, and the rate at which they worked were small. So one of the famous ones is, for example, the experiment which was used to do this loophole-free bell test with the envy centers. And that worked nicely. It was the first experiment of its type, but the data rate between the 2 remote envy centers was really, really small. I think it created data exchange once every few seconds or so. And so in 2018, or at the end of 2017, then there were 4 experiments from superconducting circuits that contributed to that work. And they were all pretty good. So Mete Atatürk from Cambridge, he also wrote a paper on that for discussing remote entanglement with semiconductor quantum dots. And so he made this graphic here that compared the performance of different physical systems. So what you see here is the Bell state fidelity when you try to entangle 2 qubits which are remote from each other, versus the entanglement generation rate and the entanglement generation probability. And when we were writing up our paper, we just checked how good we were relative to everybody else. And so here's the point for our data. Here's Bell state fidelity and entanglement generation rate. So what you could see immediately that our experiment is fast. It has a high rate. And the fidelity is also pretty good. It's not the best one, but it's pretty good. And what's maybe even more important is that the probability of creating entanglement in our experiment is really extremely good. So the first thing that you had to do is we need to extend this plot here by 2 orders of magnitude to the right to find some place for our data point. And so we have close to 70% entanglement generation fidelity, and that could be higher at reasonable high fidelity. So I think we were able to make a good contribution here. So here's these 4 other experiments. There are 2 from Yale, and I think I don't have time to really explain the details of those. There's ours, and then there's also one from David Schuster and Andrew Cleland in Chicago, which all came out at around the same time. Okay, so here's our again, this picture that I've just discussed, and sort of an electronic circuit representation of the same picture. Yeah, I think this one is for atomic physicists or so, and maybe for the general audience, it's easily accessible. And our superconducting circuit version of that is maybe it's a little bit less familiar to look at. So you have qubits, which are the atoms. You have like transmission line resonators, which you use to transfer photons, and you have readout resonators for detecting the qubit state. And in our experiments, there's about 1 meter of coaxial line between these 2 physically separated chips. And the coaxial line is interrupted in the middle, and that allows you, if you want to extract photons to detect their properties. And there's maybe some details that we could discuss further. So what is a key element for creating this remote entanglement or this quantum communication protocol? A key element is that if you have an emitter and a receiver of quantum information, the emitter has to create the quantum information, has to create the flying qubit in a way that the receiver is able to accept. And one of the ways to do that is to create a time reversal symmetric photon wave packet at the sender. And this time reversal symmetric photon wave packet at the sender, you can actually, with unit probability, reabsorb at the receiver. Well, if you just look for, say, a spontaneously emitted photon from the sender, that will have a reduced probability of being absorbed at the receiver. And there's really nothing you can do about that unless you use a sort of shaped photon wave packets. And so here's a brief explanation of how that shaping works. So in our case, our superconducting qubits not only have 2 levels, but they have a 3rd level that we call the F level. And this F level we can couple into the photon mode of a single microwave frequency resonator through this coupling field. And then whenever we have a photon in the microwave frequency resonator, it will decay from that resonator into our transmission line that sends the photon to the other qubit. And if we can control the population in this resonator excited state, where it contains 1 photon through this drive field, we can actually make this drive field control the shape of the waveform of the photon that is emitted. And what we're trying to make is these time reversal symmetric photon shapes. And we've learned how to calibrate these drive fields here in a way to achieve that. And that's what was a key element in creating this time reversal symmetry. So first we can look at whether we can emit the quantum information from our stationary qubit into a propagating photon. And for that purpose we create our emitting the sending node in its excited state. And then we run our transfer protocol, and we see that the sending node goes from the excited state to the ground state, or from a high excited state probability to a low excited state probability. And the reverse you can look at is you can look how the ground state probability increases from 0 to 1. And you can also look at whether some of the excitation gets stuck in some of the other states. And what is good, what is a thing that you can do with this interruption in our transmission line, you can actually look at the photon that travels along that transmission line. And this is a measurement of the photon wave packet, and you see that it's time reversal symmetric. And what that means is whatever pulse sequence you've used to create this time reversal symmetric photon, you can invert that pulse sequence to reabsorb that time reversal symmetric photon with essentially unit probability. And so what we can then do, rather than running this pulse sequence only on our sending node, we can run the reverse pulse sequence on the receiving node, and then hope that we can absorb this photon with unit efficiency at the receiving node. And that actually works quite well, and we've tested that for quantum state transfer. And for demonstrating this quantum state transfer, we create all possible states at the sending node and transfer them to the receiving node, and then perform state tomography at the receiving node and look at this transfer process. And ideally, this transfer process is supposed to be characterized by an identity matrix. You would just transfer whatever state you have at the sender to the receiver with preferably unit probability. Okay, so here's some example states. So if you prepare the input state in a superposition, and measure the output state, the state at the receiver. By reconstructing its density matrix, you can determine the fidelity of that state at the receiver. And you find that it's 87% in this first experiment. And if you prepare the qubit in the excited state, you find that the receiver is in that same state with a probability of 66.8%. Yeah. Obviously, this is not the thing that will create a unit efficiency quantum communication link, but it's better than anything else that existed so far because it works. This is kind of like a not post-selected in any way, but it's deterministic, and every single instance of this works. And the transfer fidelity, the process transfer fidelity is about 86%, and this is the process transfer matrix. And what you want is the identity process to be the bar that reaches as close as possible to unit transfer fidelity. And in this case, it's close to 80%. And so you cannot only transfer quantum states between these two different chips, but you can also entangle the qubits on the two different chips with each other. And what I should also mention is that we've done master equation simulations of all these processes, and we can find good agreement between what we simulate and what we measure. And so we've essentially used the same protocol to create entanglement between two remote chips, and that entanglement state fidelity is also close to 80%, and you can also use other entanglement measures. And we can understand why this is not unity, the fidelity is not unity, and there's various contributions to these infidelities that we could work on in the future. Okay, so to wrap this up, so we've just looked carefully at what all the other experiments did, and we made these tables, and they're in this paper here. With the entanglement generation rate, when it's good, when the rate is high, and you see there's maybe 8 orders of magnitude difference between sort of the fastest and the slowest experiments. And we come in pretty high on this with the entanglement generation rates of maybe, or with communication link rates at about 50 kilohertz now, but we think we can do that also at a megahertz rate. The current fidelities and concurrences are pretty good. Yeah, they're high, but not the highest in this field yet. And so we also have thought a little bit about how to improve that, and improving our coherence, which was not terribly good in these devices, will help. And we've also worked already on using heralding schemes, which are then not deterministic, of course, but which will bring up the fidelities of the transferred states. So we were pretty happy with that. And again, I think what would be interesting to see is to evaluate whether such a technique would really then allow you to extend the capabilities of quantum processors. If you have a number of qubits on one chip, a number of qubits on the other chip, and if these qubits could communicate maybe through an as wide bandwidth as possible quantum channel between them. Okay, so just to remember you of the different results here. So we have this fast readout, we have the fast reset. This whole idea is multiplexable. We can do experiments for error correction with that I didn't talk about. I've shown you this kind of high data rate, good fidelity transfer protocol, and essentially through some inversion of these processes, you can also turn this into a very good QND microwave frequency single photon detector. Yeah, and with that, I'd like to thank you for your attention. Mention that really to bring this further, what is needed is quantum engineering. Yes, we need to bring engineering and physics together to make progress on these circuits. And ETH actually, as of fall this year, has a quantum engineering master's program that we've just started, and with that we hope we'll have more people interested and provide sort of more qualified students to work in our labs, and also to work with the startups and the industry that is developing in this area. Okay, with that, I'd like to thank you for your attention and thank our team at ETH for working on these subjects.